Hello. Just letting you know I'm here. We'll be starting in, I don't know, 10 minutes or so. Hello, everyone. Can you hear me?
Yep.
Yes, excellent. Okay, I also need to turn up the volume so I can hear you if you talk to me. That's better. Excellent. All right, so I thought I would start out by just seeing if you guys have any questions about what's happening this week or anything that you would like to know about. And if you don't, then we'll just get to the lesson. Ah, look at that. It's just like in regular class. Is it an actual, let me see. Is it an actual school week? No, it is not. So this is Ms. Spence being a little bit crazy. Technically, if you all want to tell me to bog off and you don't want to do chemistry this week, that's totally fine because classes are not running this week. My feeling was that probably it would be a good thing for you to have covered more of the chemistry 12 material than less of it. So I guess I should ask, do you actually want to do this week? If you really don't, then we can, the teachers are at school. Yeah, we're, hello from Burnaby Mountain, sitting in our classes with nobody in them. Super exciting. Do you want to do this? If you don't, if there's like a resounding majority who are like, forget it, I can do without some of this material, I don't mind going off to university without it, then we can bag it. What do you guys think? Don't mind learning? Okay. Anyone else got an opinion? You can always share to just me if you are not comfortable sharing with everyone. Okay. Anyone else got an opinion? Okay. Nobody so far has said, let's ditch this. So I'm happy to go ahead with it. So I guess one last thing before we start, is 12 o'clock an okay time for people, or would we like to move it to a different time? Is 12 o'clock okay? Okay, and if there's any of you who have something else going on, the meetings are being recorded and I will post them. Okay, so sounds good. In that case, let's not dilly-dally. Yeah, I just said dilly-dally. Let's get to 5.1a, which is an introduction to acid-base indicators. Can you guys see the chat on my screen, or is that just something I can see? Because it's kind of like blocking me, but I'm okay if it blocks me as long as it's not blocking you. No, you can't? Okay, good stuff. All right, so I'm just gonna take that over to the side there so it's not blocking me too much. Good. So this is, I'm calling this unit 5, it's acid-base part 2. You're going to be tested on both of them together on that Wednesday, Thursday, the last Wednesday, Thursday of the term. Intro to acid-base indicators. In general, hopefully you know this already, indicators are substances that change color in the presence of other chemicals. And just in case you are unaware, this presentation is posted on Teams, both in a filled in form and in a fill in the blanks form. So you can just grab it later if you don't have it on you right now, okay? So what is an acid-base indicator? An acid-base indicator is actually a weak conjugate acid-base pair. It's not a single chemical. it's both members of the conjugate acid-base pair. It will have one color in its protonated form, which we're going to call HIN, IN for indicator, and it's going to have a different color in its unprotonated form, IN minus. You guys can see my screen, right? Just double checking. Yes, okay, good. Acid-base indicators will change colors at specific pHs or pH ranges. And this is just a little picture showing you that indicators have really complex structures. For example, this is the structure of brom cresol green. So you can see why I don't actually want to write the entire formula for brom cresol green, because that's ridiculous. So often what we'll do is, instead of writing that whole big thing out, we will instead write HBG for the acid form of the indicator. And it turns out when this thing has a proton on it, which you can see that proton right there, okay, and you can see over here it is missing. When it is protonated, it is yellow. Has to do with the ring structures. You don't need to know anything about that, okay? But when it is unprotonated, when there is no proton here, then it's going to, we're just going to write Bg minus, Bg for brom cresol green, okay? And that form is actually the color blue. And you need to have both substances in order for this to be an indicator, because otherwise it would just be all yellow or all blue. You need it to be able to transition between the two of them. Okay, so sometimes we'll use like little abbreviations like BG for brom cresol greens. Other times we'll use IN or IND just for indicator, just so that we don't have to write out those nasty big formulas. I'm drawing your attention once again to the fact that I've been bolding the pair when referring to the acid-base indicator. It is not just a single species, but both members of the acid-base pair together that make up the indicator. Okay, so brom cresol green is HBG and Bg minus together in an equilibrium system. It is not just HBG. It's also important to notice that all the indicators are weak acids. Okay, weak acids and weak bases. Weak acids and weak conjugate bases. Because if they were strong, well, if you have a strong acid, it just gives up all its protons, and now you just have the base form. And so it couldn't turn into its acid form. And so if we had our brom cresol green there, and it was if HBG was a strong acid, it would all turn blue, right? It would all turn blue, and we would never get any of our yellow form back. And so that's useless to us. So all acid-base indicators must be weak acids and their weak conjugate bases. All right, so reiterating here, we have HBG, which is the acid form, and it is yellow. We have Bg minus, which is the base form of the indicator, and it is blue, and we get this equilibrium here. Okay, and so all those three substances are present in the beaker. Okay. Now, if we have an acidic solution, and concentration of hydrogen ion is high, what would that cause the equilibrium here to do? Would it be shifted to the right, or would it be shifted to the left? Yeah, it's going to be shifted to the left because, of course, we're going to have the hydrogen ion is high, and so it's going to shift it to the left. And if it's shifted to the left, Is our concentration of HBG high or low? HBG, high or low? High, yes. Okay, so concentration of HBG is high, and that means that conversely, the concentration of BG minus is going to be low, okay? And what that means is that we can say that HBG is the predominant species. This is a word you're going to have to get to know because it comes up a lot. I will keep reminding you that predominant just means main. So HBG is the main species, and remember HBG is yellow. So therefore the overall color of the solution in acid, when it's shifted to the left, what will the overall color of the solution be? In acid, when it's shifted to the left, it will be, yes, yellow. Okay, excellent. Why is bromcresol green blue? Why is it blue in basic solution? Well, looking once again, here we have our blue and we have our yellow. In basic solution, we have lots of OH present. Yes, because it is basic. And of course, we know that OH reacts with H plus. OH minus reacts with H plus. What do we get? What do we get when we react OH with H? We get water. Yes, excellent. Okay, so we have water, and this causes the H plus to do what? What happens to our concentration of H plus when it reacts with the OH minus? It causes it to decrease, yes. Okay, so that is excellent. So hydrogen ion concentration is decreasing. Which way is our equilibrium going to shift? System is going to shift right. Yep, and that's going to make our HBG concentration, if we're shifting to the right, HBG is going to be high or low? Low, and that means that BG minus is going to be high. So what was that word that we used for main? What's the word we just used meaning main? Starts with P. Predominant, yes. Oops, I should have started over further. Predominant. And who is the predominant species when we are in basic solution? And the system is shifted to the right. BG, yes, BG minus, BG minus. That conjugate base form of the indicator. And therefore the overall color of the solution will be blue. Okay. Indicators transition between colors when the acid form, for example, HBG, which is yellow, and the base form, BG minus, which is blue, have similar concentrations. What that means is that we have both yellow form and blue form present. Both yellow and blue present. What color will bromcresol green then be if it is transitioning between its acid form and its base form? Yeah, it's going to be green. Hopefully you guys know your color combinations. Yellow plus blue makes green. Excellent. Okay. Now, when we have, you're going to have different shades of green depending on where you are in the shifting process, right? You can have like a bluey green, and then you're going to have a yellowy green. But at some point, you're going to have the acid form concentration being exactly equal to the base form concentration. And what we do is when we get to that point, we call it the transition point. Okay, that exact equality point. And it's where the color of A is equal to the color of B, because the acid form concentration is equal to the base form of the concentration. So we can define transition point then as the point for an indicator where the HIND concentration of the acid form is equal to the concentration of the base form. Now, we get into some pretty cool stuff here. I like this because it's fun, just a little easy math that makes some other things equal. So consider this indicator. If we have HIND in equilibrium with H plus and IND minus, we can write a Ka for it, which of course is our hydrogen times our IND minus divided by HIND. Here we go, right here. Now, we just decided that at the transition point, the acid form and the base form concentrations are equal. And if they are equal, we can cancel them out. Yes, so we're canceling it out here and we're canceling it out here. And the only thing we're left with then is Ka equals H plus. So at the transition point, not only is HIND and IND minus equal, but also the Ka of the indicator is equal to the hydrogen ion concentration. Okay, and it follows from that that the pKa of the indicator is equal to the pH at the transition point, because of course, if we take the negative log of the entire thing, yes, so we'll end up with the negative log Ka equal to the negative log of H plus. And we know when we take the negative log means that we now have a P, yes? And so we now have pKa of the indicator is equal to the negative log of hydrogen is the pH. Okay, so we actually have three things that are equal at the equivalence point. We have one thing that is equal, this is number one, okay, that's equal at the equivalence point, the two forms of the indicator concentrations. The second thing we have is that Ka is equal to H plus, Ka of the indicator is equal to H plus. And we also now have the third one, and that is that pKa of the indicator is equal to pH. And all of these three things are true at the transition point. So this allows us to do a few things. So if I give you the Ka of the indicator, you can then find the pH at the transition point, because you know that Ka of the indicator is equal to hydrogen at the transition point. And from, if you have hydrogen ion concentration, you can complete that process and then convert your hydrogen into pH. Okay, so pretty straightforward. If I give you Ka, you know that's hydrogen, and then just convert it into pH. Second thing, you can do the opposite process. If I give you the pH at the transition point, which we are going to call the pHTP, a lot of letters. pH at the transition point, then you can find the Ka, because we know that we can take pH and convert it into hydrogen. Do you remember the formula to convert pH into hydrogen? If you remember it, you can just type in yes, you remember it, because it's hard to type in like what it actually is. But if you think you remember how to find hydrogen from pH, you can just type in yes or yep or something. Yeah. Okay. It is 10 to the negative pH, or if you prefer, you can write it like this. H plus is the antilog of the negative pH, which reminds me, I haven't quite finished marking your quizzes yet, the pH quizzes, but they are looking really good, okay? And they should be done in the next day or two. All right. So we can take our pH at the transition point for an indicator, and we can find hydrogen using our formula here. And then we know that hydrogen is just equal to the Ka. So once you know hydrogen, you know Ka. Pretty easy. If you happen to have your data booklet on you, you can go check out page 7, which lists the following things. We have the indicator, the pH range in which the color change occurs, and the color change that actually does occur. And I'm just going to grab our data booklet here so that we can take a look at it. Move my chat because it's blocking my view. There we go. Okay. So you can see this is what the entire chart looks like. I probably won't bring this up because on the sheet, I just have like little segments. So if we're going to say, for example, if we're looking at methyl violet, which is I think the first one we're going to look at, I'll just have this part of the table pulled up. Okay, so back to here. Go. And here we are. Oh, look, yes, I do. First one we're going to deal with is methyl violet. So let's try this example. What is the pH at the transition point for methyl violet? Well, remember the transition point. What is the transition point? It is when it's the point where concentration of the acid form of the indicator is equal to concentration of the base form of the indicator. And in other words, it is where the concentration of color 1 is equal to the concentration of color 2, because the acid and base form, of course, have different colors. So color 1 and color 2 are equal, so we are transitioning. And for methyl violet, we are transitioning from yellow to blue, okay? So we're going to take a look at a little pH scale here and translate what's on the chart onto a pH scale. So here is our pH scale. Okay, we got our line here. And you can see I've marked on it 0 and the 1.6. Yes. And if we are above 1.6, anywhere above 1.6, we're going to be blue. If we are below 0, I should have done the color the other way. Oh, I'm going to change it. If we are above 1.6, we're going to be blue. If we are below 0, we're going to be yellow. Okay, and so what that would look like then on our pH scale is anything in between 0 and 1.6 is going to be green. because at that pH, you're going to have a mixture of the acid form of the indicator and the base form of the indicator. I should have highlighted those in their appropriate colors, because if we have yellow and we have blue, then we get green. So in the range from pH 0 to 1.6, we get a green color. Down at close to 0, it's probably going to be kind of like a yellowy green. Up near the top, it's going to be a bluey green, right? As you get more and more of the blue MV minus present. However, if I ever ask you what color is this indicator at, say, pH 1, which is in there somewhere, I don't want you trying to figure out whether it's yellowy green or bluey green or whatever. Anywhere in between 0 and 1.6, just say green, okay? So don't worry about trying to give me different shades of green depending on where it is. If it's in between those two values, it is just green. If it's actually sitting on the value, I'm not going to ask you that, because I think that's an unfair question. Because when does this solution, you imagine you're sitting there, you did a titration, right? And you're like, okay, it's changing color. And it was really nice when we did phenolphthalein, because it changed from colorless to pink, and you could see definitely, oh yeah, there's a pink color and there wasn't before. But if we're switching from yellow to green, when do we stop being yellow, 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 yellow? And when do we become very yellowy green? Like I just can't. So I'm never going to ask you what is the color of cresol green, or sorry, methyl violet at pH 0. So don't worry about these numbers here and what color are they. Is it green? Is it yellow? Is it blue? Oh my God. Just worry about like kind of the edge, the zones. You just need to know the pH of the zones. So below 0, it is yellow. In between the two pHs, it is green. And then above pH 1.6, it is, okay, there we go. Now, thinking about what this means in terms of pH, if we have a low pH, that means our concentration of hydrogen is high. And if our concentration of hydrogen is high, we are going to have the protonated form. Another word for you to know there, the protonated form, or the acid form of the indicator, is the predominant form. That means we mostly have the yellow HMV. Now, as we move up to a higher pH, if we have a higher pH, that of course means that we have a lower concentration of H+, which means that, oh look, there's no H there because the H is lower, there's not as much of it, that equilibrium is shifted away from the hydrogen, okay? And so when you're on the upper side of the scale, this is going to be your base form, and when you're on the lower end of the scale, that's going to be your acid form. So if we were to look at this, we could label on here that this is our base form, and this is our acid form. Okay, so the base form is blue. Base form is always going to be on the right of that table. The acid form is yellow. It's always going to be like the left-hand value of those two. Okie dokie. The transition point, the actual official transition point, occurs at the midpoint. Okay, right in the middle of that transition zone. And so we can find the pH simply by taking the average of those two numbers. So the pH at the transition point is simply going to be equal to 0 plus 1.6 divided by 2, and we get 0.8. So the pH at the transition point is 0.8. Put some stars here. So don't forget, that tells you find the pH at the transition point by averaging the two numbers at the ends of the pH range of the color change. Okay. What is the Ka of methyl violet? The Ka of methyl violet. Well, we now know the pH at the transition point. Yes, which is nice. So we know the pH at the transition point. And we also know that at the transition point, the Ka of the indicator, so that's going to be the Ka of methyl violet, is equal to the concentration of hydrogen at the equivalence point. And that's because if you have forgotten why that is, it's because at the transition point, the concentration of HMV and MV minus, the acid and base form, are equal. So we can cancel them out and we are left with Ka is equal to hydrogen ion concentration. Doing the math is like super easy because you're just doing stuff on that quiz from before break that you're doing really well on so far. So pH is 0.08. We can use our formula H plus is equal to 10 to the negative pH. And so H plus is 10 to the negative pH, showing all my work. You know, I got my formula, and then I plug in the value, and then I get 0.2 molar. That is my concentration of hydrogen. And that number is the same as our Ka value, but of course for Ka, there is no. We like that? Is that straightforward-ish? Yeah? Okay, good stuff. Another way of showing the work, if you prefer, sometimes this is a little faster, just depends on how you want to do it. You know that in addition to H equaling Ka at the equivalence point, pH equals pKa at the, not at the equivalence point, at the transition point. So we know that pKa is 0.2. Did I say 0.2? No, that's so wrong because the pH was 0.8. Oh, sorry about that. Okay, scratch that out. 0.8. Here it is. pH at the transition point is 0.8. So pKa is equal to 0.8. And what that means is that our Ka, and I'm going to write it bigger just, you know, because I can, is equal to 10 to the negative pKa, just like hydrogen is equal to 10 to the negative pH. Ka is equal to 10 to the negative pKa. And so we plug that in there. Oh, and I got the value right here. That's good. 10 to the negative 0.8, and we still get 0.2. So either way of showing the work is fine. I don't care, whatever you like. Pick one that works for you. Okay. All right. So taking a look at this one, this is just reviewing the concepts. So I want you to try and answer these for yourself. If you're, you know, feeling up to it, you can type your answer into the chat. What color is the acid form of phenol red? What color is the acid form of phenol red? We have two choices. We have yellow or we have red. Those are the two colors that phenol red is. And yeah, a lot of people are putting yellow in there, which is absolutely correct because it is yellow when the pH is lower. okay? Which means we are going to be in the protonated form because lower pH means higher hydrogen. Okay, and vice versa. When we're at the higher pH, we're going to see that red color, and that means we have the lower ion. Totally lost my train of thought there. We have the higher pH, which means we have a lower hydrogen ion concentration. That's what I wanted to say. Lower hydrogen ion concentration. So remember the one on this side, this is always going to be the acid form of the indicator. And the one on this side is always going to be the base form. So the acid form of phenol red, we can say, okay, that's going to be yellow. And that means, what color is the base form? Well, obviously it has to be red. What color will phenol red be at its transition point? Yes, it's going to be orange. Hopefully you all know your color combining. Like I said before, if you don't, go back and talk to your elementary school teachers and say, hey, what were you doing? If you don't know them, get yourself a cheap set of watercolor paints and have some fun mixing them up, okay? Now, I would like you to try this on your own. I will give you maybe 5 minutes to do this. I would like you to find the Ka of phenol red. Do you think you can do it? See the elevator music for you. I got some answers coming in. Feel free to type it in if you think you have an answer. And remember, I want the Ka, not the pKa. And if you're stuck and you're like, I don't even know what to do, find your pH at the transition point. A good starting place. Take your two values, 6.6 and 8.0, divide by 2. What does that give me? a little cheat sheet here, 7.3. Okay, so that is our pH at the transition point. So we could say that we know that the pH at the transition point is the same as the pKa. So this is also equal to my pKa. And if I want to find Ka, my formula would be 10 to the negative pKa. Okay, so this is one way of showing the work. I'll show you the other one in just a moment. So we would get then 10 to the negative 7.3, which equals 5.01 times 10 to the minus 8. But now we have to ask ourselves about significant figures. Oh, okay. How many sig figs should we have in this answer? Being that we are starting with these two values here, the numbers we're starting with. How many sig figs should we have in our answer? And remember, these values here are pHs. And what do we know about sig figs and pHs? Only digits after the decimal are significant, because the digits in front of the decimal are telling us what the power of 10 would be when we're talking about the hydrogen ion concentration. Okay, so these are the, remember, like the 6, the first 6 and the 6.6, that would be like 10 to the 6. And the 8 would be like 10 to the negative 8. Okay, so there's just one sig fig in both of those numbers. And so our final answer then, we should round to 1 sig fig. So that's our Ka then is going to be 5 times 10 to the negative 8. Boom, 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 boom. Okay, good stuff. And let's see, the other way of doing it, if you don't like doing it that way, you're like, I don't know, this 10 to the negative pKa thing seems weird to me. You could simply say, okay, well, I'm going to, instead of doing that, I'm going to say that my concentration of hydrogen at the transition point is equal to 10 to the negative pH at the transition point, which is equal to 10 to the negative 7.3, because we're going to use that same value. It ends up, I mean, it's all the same math, right? It's just a different way of showing the work. And we get 5.01 times 10 to the negative 8. And that means that Ka is equal to H plus at the transition point, which is equal to 5 times 10 to the negative 8. So either way, whatever you like. Okay. All right, one last question and then we are done for today. The Ka of an unknown indicator is 3.2 times 10 to the minus 5. The acid form of the indicator is red. The base form of the indicator is blue. What is the color of the indicator at its transition point? So we have the acid form of the indicator is red. The base form of the indicator is blue. And what do we get when we mix red and blue? We get, yes, purple. Excellent. Red plus blue equals purple. At what pH does the indicator change color? Well, if we know that it's changing color, what point is that? The point where it changes color. That is known as the what point? transition point, yes. And we know that the pH at the transition point is equal to what? Concentration of, let's see. pH isn't equal to concentration of hydrogen. It's equal to the pKa, okay? pKa of the indicator. So again, there's two different ways of showing this work. I'm just going to show you one of them right now. I think actually, have I shown? Oh, I've got both of them in the answer key. So I'll see if I can cram them both in here. So this is going to be, let's see, pH at the transition point when it changes color is equal to pKa. And so that's the negative of the log of Ka, which is equal to 3.2. Oops, not 3.2, negative log of 3.2 times 10 to the minus 5. And we get, what do we get? 4.49. Okay, if you prefer to show your work the other way, you can say that, and I don't know, you can look it up. I'll let you look it up in the answer key if you want to see the other way. This is the easiest way to do it. Okay. What color is the indicator in 1.0 times 10 to the negative 6 molar HCl? So an easy way to do this is to find the pH of the HCl solution and compare it to the pH at the transition point. Yes? So we now know the pH at the transition point, which is 4.49. And hopefully you remember that HCl is a strong acid. It is our most famous of all strong acids. And so it dissociates completely. HCl goes to H plus, one-way arrow, one way. So all the HCl turns into H plus, HCl minus. And so the concentration of hydrogen is the same as the original concentration of the HCl. And so that is 1.6 times 10 to the minus 6 molar because it is a 1-to-1 ratio. So to find our pH, of course, we take the negative log of H. There's our negative log, and we end up with 6. So our pH is 6. Okay, so the pH is 6. And the pH at which it changes color is 4.49. So if I draw myself a little diagram here, where I have 4.49 is the pH at the transition point, I have been told that in the question, where did it go? The acid form of the indicator is red. And so below 4.49 in a more acidic pH, I'm going to have the acid form of the indicator, which is red. Above 4.49 at a more basic pH, I'm going to have the base form of the indicator, which is blue. And of course, that means that at pH 6, the indicator will be blue. And if we needed to say, what is the predominant form? What is the predominant form? It is the IND minus, the predominant form. And I think that is it. Yes, it is. So your homework then would be number 1 make sure that if you have not caught up on anything from over the break, that you catch up on anything that you didn't catch up on, because that's, you know, you can't go forward until you've, you know, got your basic stuff all set there. But yeah, just this worksheet, 5.1a. Yeah. That's it. 5.1. Okay, finish anything you didn't do over the break. Are we all good for doing this again tomorrow? All right, I will see you tomorrow then. Enjoy the snow that's out there. It's a beautiful day. Take care. Hope you're all healthy. Hi, I'm good. Happy New Year. Let me find my mask here. There we go. It was good. Not long enough, but it was really good. I was thinking of you over the break because I don't know what you have. I know you have Chem 12 coming up. I've been told myself to stay. Do you have something you're already wanting to do?
Oh, I actually just got picture blue, and she's gonna order me. Perfect. Okay, good, thank you. Yeah, I was gonna do it all myself, and then last week I had enough. This actually, no, have something that yeah, we all have it. Yeah, yeah. In order to kind of like get people's handos that they really want. Oh yeah, this is my first step. So you're gonna ask me one question? You ask a lot of questions, which I'm good at. When I ask, like, what happens if my kids look at stuff? Oh, good question. I was like, I mean, what happens? I don't know, like, that was the first thing that occurred to me. Yeah, but I mean, people like, if my grade, like, I like people all day. But what do you do? He does get a video game. That's what you do. In 5 minutes. Yeah. When I finish this level, oh, but there's no examination right now. What are you doing? No, they are a lot better, but universally they're global. Yeah, and back in the day, I know, right? Yeah, like when I was in university, yeah. And it would always be like, oh, let's just have one more game. Like, oh, let's maybe after one more game, one more game. Yeah. Yeah, that I know. Because I feel like they're motivating to know that. Yeah. Are they doing it like in the States or somewhere or yeah, or like, no. I don't know if it's playing all the time, but I thought I'm using the iPad out of separating my package downstairs. And it, my oldest son Discord. There's that like Discord notification thingy. Now he's marking. Friends are messaging on Discord at fucking night on a school night. Like, you guys think it's something good? Yeah. Yeah. I mean, I talk to my friends, the ones who look after everything. Yeah, like, how do you get that last night? How are you? Yeah. Well, I know it's not like your mom, but you would. Yeah. For you. For growing. You do it. And he was like, yeah. And he was like, answering questions. I'm like, oh, you're good. I'm like, okay, then we're going to do that every day. Oh my God. I'm not even buying into that. Promise me. Oh my goodness, I just love this. Like, it was supposed to be an hour. It ended up being whatever. It's a lot more than usual. Okay. I do love watching gameplay video games. I don't even know what it's doing. I can play it. And I'm like, I can't do it. Like, it's not my problem anymore. No, it's yeah. I mean, we're great neighbors to each other. Like, but then when you decide to, yeah, you're right back and forth. But then ultimately you're better than like you guys. Don't have a choice. You like it. Yeah. Yeah. I don't know if it's early. And they would like climb up to the line. And once the lines go by on the side of the road, and you know, how the line would actually look like it off the road. They always do it like really. So they didn't have blood. We don't have. Like, man, that's for always a year. Like, really? A year. So maybe having the other. There's not the same word. I asked them, I said, what is it? I didn't know what was going on, so I said, and I'm like, feel free to like use it directly to me, not to the whole audience. Right, rather than not knowing. And we don't know if we're going to get it at the end or whatever. Yeah. Okay.
Oh, I didn't end the meeting.